Okay. So we will start a new topic today, which is communication in distributed systems. This is chapter 4 of the book. Okay, so we have covered a fair bit of ground already. 3 chapters are done. So that's why there is going to be a homework just to make sure you keep up with the class, because there's quite a bit of material we are covering here. So this is going to be chapter 4, which is going to focus on the networking aspects of the communication aspect of distributed systems. We will start with a more traditional discussion of RPCs and RMIs. Some of you may know something about that already. And then we will build from there on, talk about distributed objects and object-oriented systems and that can be used to drive distributed application. Okay. So today we'll just start with a very basic background on networking and RPCs, which are remote procedure calls. I'll explain what they are and how they work and so on and so forth. Okay, so let's start with communication between processes. Okay, if you have two processes and they need to communicate with one another, there are two ways this communication can be enabled. You can use what is referred to as unstructured communication or structured communication. In unstructured communication, you are either using shared memory, shared memory buffer that processes can read and write. Okay, so they can basically put some object or data into a shared buffer. Some other process can come and pick it up, and that's how they can actually interact with one another and pass data between one process to another. Okay, so you can either use shared memory or shared data structures. That is referred as unstructured communication, because the structure of how the communication occurs depends on the application and the application designer. Structured communications involve sending messages, explicit messages back and forth. This is also referred to as IPC or inter-process communication. Okay. So you can send a message from process A to process B, process A to B. B can send a response back and so on. Okay. Most communication that we will talk about will be of the structured kind. Okay. Now, if you look at distributed systems, you can also have these two forms of communication, but we will also require OS level support for networking in there. Okay. Now, this discussion of structured and unstructured communication, you can assume the processes could also be on the same machine and they still communicate using structured or unstructured, okay, methods. Now, when you have a distributed system, these processes will reside on independent machine, not on the same machine. If they have to communicate across machines, you will need a form of communication medium, which is typically a network of some sort. Okay, this is why if you have these processes on the same machine, you don't need networking support. Okay, you can simply use messages, but the messages don't go out of the machine. They're just going from one process to another on the same machine. Okay, but in a distributed system, you will need networking. So I'm going to give a very quick overview of networking. I'm sure many of you have some sort of undergraduate networking background, so this may just be repetitive. So I'm going to go through this quickly. Okay. So you do know what a protocol is. Protocols are essentially rules for communication between processes. Any process that needs to communicate with some other process needs to agree on what rules are going to be followed for communication. These rules are typically specified in what are referred to as protocol. That's the language for communication. Okay, there are different kinds of protocols. Okay, the way typically you have a networking stack in an operating system is you will have different layers in the networking stack, and each layer has a specific protocol that allows it to communicate with a peer layer on some other machine. Okay, so in this case, this is machine A and this is machine B. This is the networking stack on machine A. That's the networking stack on machine B. The networking stack, as you will see, is a layered stack. Okay. There are layers, and there are these protocols that operate at each layer. If you think about the common protocol stacks like TCP/IP, they will be structured in this form, as we will see on the next slide as well. Okay? So this is a standard ISO protocol stack that we learn in any undergraduate networking sort of course. I'll just quickly talk about what they mean. Okay? So you will see 7 layers here. Okay? What is at the very bottom is the physical layer. Okay? This is the actual medium used for communication. If you have Ethernet, that physical layer is a wire. Okay? If you are wireless, the physical medium is air. You're actually sending the wireless, you shouldn't say air, it's actually the wireless channel that is being used for communication over the air. Okay? So this is the physical medium, and you have physical protocol that basically allows you to send packets out on a wire or send packets out on a wireless channel and so on. Okay? Above the physical layer is a data link layer. This is also referred to as a MAC protocol. You've heard of what MAC addresses and so on. So this is the protocol that may be used to construct a data packet using Ethernet, or it could be cellular, or it could be Wi-Fi. All of those protocols are actually referred to as data link layer protocols. Okay. The layer above this is the network layer. Okay. Network layer is responsible for what is referred to as hop-by-hop communication. Okay. This is where packets get routed over a network. Okay. If machine A sends a packet or a message to machine B, okay, something in the network has to make sure that the packet eventually reaches the destination. And this process is referred to as routing. And typically the most important function that a network layer protocol provides is routing. Right? In the TCP/IP stack, this is the IP layer. Okay. Transport layer, so network layer does hop by hop, one hop at a time communication. Transport layer does end-to-end communication, is responsible for end-to-end, which means there are senders and receivers. There may be multiple hops in between, but as far as the transport layer is concerned, it just basically focuses on things like when a packet was sent, was it received at the other end? If it was not received, should we retransmit that packet? At what rate should you keep sending packets so that they get there as efficiently as possible or at the highest rate as possible? All of those decisions are made at the transport layer. Okay. The protocol that is used there is basically going to be responsible for things like recovering lost packets, retransmitting them, deciding on the rate and so on. In the TCP/IP stack, TCP is the transport layer protocol. It's referred to as transmission control protocol. UDP is also an example of a transport layer protocol. And then on top of this, you have session layer protocols, presentation protocols, and application. In the TCP/IP stack, typically there aren't any session and presentation protocol. Applications run directly on the transport protocol. You can write an application that opens a TCP/IP socket and starts sending data. Okay, but in the ISO protocol stack, you do have something called a session layer, which establishes user session. It's a session that's established, and over the course of the session, multiple packets may be sent from the sender to the receiver. Okay. Presentation protocol may be responsible for user level issues. How do you present the data that has come to you? Right? And application level protocols are simple applications. FTP, HTTP, SCP, all of those are examples of application layer protocols. Okay? So those are actually protocols that basically one application here talks to the other application there. They speak, let's say FTP, or some other. SMTP is the mail protocol. Right? Simple mail transport protocol. HTTP is hypertext transport protocol. Those are all application layer protocols. Okay. Anyone have questions? I'm assuming most of you know this, but if you didn't, this is the time to ask questions, because I'll assume you know this in the subsequent slides.
So it's the difference between physical layer and the data link.
What's the difference between physical layer and data link layer? That's the question. Okay. Physical layer is the actual medium used for communication. The data link layer is the protocol that is used for communicating over that physical medium. Okay, so in this case, the physical medium may be actually the wire itself, and it may need some or the wireless channel. So like in the Wi-Fi case, for instance, you may transmit on 900 megahertz or 2.5 gigahertz. So that channel is basically going to be your physical layer. Now the data link layer is responsible for constructing a packet, or what is referred to as a frame, really, and sending it over that medium, ensuring that when it gets at the other end, there was no errors in transmission, that the data was not corrupted and things like that. Okay? And if there are collisions, if this is a shared medium, if there's a collision, the data link layer will be responsible for backing off and retransmitting and so on and so forth. Okay? So think of this as the actual channel for communication, and this is the protocol that runs over that channel. So if you heard of 802.11, A, B, C, all of those would be data link layer protocol. The channel uses 2.5 gigahertz or whatever, 5 gigahertz channels. Those are all the physical layers. So that's the channel that is being used. Any other questions here? Okay. So this is a very sort of simple picture of how data flows down the protocol stack. So typically the way protocol stacks operate is the application is the one that wants to send a message to the application at the other end. So it will construct a message and hand it to the protocol stack below it. Okay? So that packet or the message will be is referred to as a packet, or can be broken down into smaller packets, will flow down the protocol stack. It will be sent over the medium. It may traverse multiple hops or multiple routers along the way and eventually appear at the destination. Okay? The OS will then keep processing it and send it up the protocol stack and eventually deliver it to the application. So packets go down the stack, go out of the machine, arrive at the other end, go up the protocol stack and are delivered. Okay? So in doing so, you have this original message that needs to be sent from one end to another, and each layer in the protocol stack is going to process the message and maybe add some header or footer information to the message and hand it to the stack protocol layer below it. Okay, so you can say here is the message, and then let's ignore the session and the protocol. So if you hand it to TCP, okay, in the TCP IP stack, it will take the message and stick on a TCP header onto it. When you hand it to IP, you will add an IP header. IP header will include the source IP address, the destination IP address, the source port number, destination port number. All of that information will be in the header information. It's not in the message. The message may simply be a string that you're sending somewhere, or an email message you're constructed. That's the email. And then you will have header information that gets added. Okay, in the email case, the email headers will be your SMTP header. All those the from address, the destination, all the mail headers will be in the application layer header. Then there will be a TCP header, there will be an IP header, and you will basically hand the IP, let's say, to Wi-Fi or cellular or to Ethernet, and you will have an Ethernet frame header, which is the data link layer header, and then it will go out over the medium. Okay? When it arrives at the other end, okay, you will get all of this. The packet has a bunch of headers to it. So then each protocol layer, stack layer, will look at its header and decide what to do with the packet. Okay, the Ethernet header will say, is the packet arrives, is the right machine, and so on. And then it will strip off the header and hand it to the IP layer. The IP layer will look at what's the destination address. Should I forward it further on, or is this the machine that is supposed to receive the packet, and so on. Okay, so all these headers get stripped off and eventually hand whatever was sent by the application to the other endpoint. Okay? That's how protocol processing is going to work. Okay. Any questions here? Yes.
The book stated that a lot of times applications do not faithfully implement the ISO layer model.
Yep.
Like, how often is this model used fully in practice?
Okay, question is, the book stated that the ISO model is not used in practice, and how often is this actually used? So that's a conceptual model, okay? The reason it is not used in practice is there were protocols that actually had all of those layers of the protocol stack, but the de facto standard is to use TCP/IP to communicate. TCP/IP basically only defines the layers until the transport layer, and it leaves all these other tasks to the application. Right? So in some sense, it's not that those functions are missing. It is the responsibility of the application to implement whatever it needs to implement. Okay, as far as so. A good example is you may be running HTTP as your application layer protocol, but if you want to set up a secure connection, the SSL part of it will be either in the session layer, for instance. Right? But there is no real session layer protocol in TCP/IP. The application is doing both HTTP as well as SSL. Okay, so everything here is now grouped into, you can think of it as in the TCP/IP world, everything about TCP is the job of the application. So if you need a presentation protocol, go ahead, implement it, but there will not be one provided for you. So the answer is, it is not often the case you will see all of those. The functions are there, but you will not see a layering about the transport protocol, because all these functions are now become applications' responsibility. Okay, so they are there, but not clearly as those layers. Everything below TCP looks exactly the same. Okay. Any other questions here? Okay. So, because this is coming back to the question that was just asked, because there is no presentation and session layer protocol in this course, since we are interested in developing distributed systems, we will actually try to implement some of those functions into a layer called the middleware layer. Okay, so above TCP, you will have a runtime system which will be your middleware. That is the one that's going to provide higher level services to the application. That will speak some middleware protocol which will be the equivalent of whatever happens in the session layer or the presentation layer, or actually something even more sophisticated than that. So we will basically assume that TCP/IP is given to us. That is something that comes out of any network protocol stack. What we are going to focus on is what middleware protocols you need to implement interesting distributed applications. And also all of the things that we are going to talk about subsequently, you should assume run here. Okay? Or you can implement them in the application, but then to simplify it, you can use a middleware that will implement those functions for you. Okay? Is that clear? Okay, so we will talk about many different systems. We'll talk about distributed commit and consensus, and today we are going to talk about remote procedure calls. Those are all examples of some systems that run over TCP. They assume that TCP/IP exists, and they implement a middleware layer on top of which you write application code. Okay, so before we move on to talking about remote procedure calls, I just wanted to provide some flavor of what TCP actually does for typical client-server applications, why it is not the most efficient way to do things, and there may be better ways to actually optimize the use of TCP. Okay? Although those better ways are not yet used in practice. So let us take a typical client and server application. The typical model for communication is client sends a request to the server processes the request, sends back a response. And that's a very common method, because you can think of a browser sends a HTTP request, server sends back a HTML page as the response, or you ask for a JPEG image or whatever. So there's a request response type communication pattern that you will see. Okay. To implement that request response pattern, this is what is going to happen at the TCP layer. Yeah, first of all, when the client wants to send a message to the server, the request has to go to the server, you have to establish a TCP connection, a new TCP connection, typically. Okay. So the way TCP works is you have this three-way handshake. I don't know if anybody knows what three-way handshake is. That's the standard way you establish a TCP connection. Okay. This requires you to send what is called a SYN packet from the client to the server. SYN basically says, I want to establish a new connection. Okay. Acknowledgement comes back. Okay, and by the way, since the communication is bidirectional, okay, the server has to send a SYN packet back saying, I want to communicate back with you as well. So you'll see a SYN going and a SYN coming back. Okay? And then an ACK for the SYN comes with that packet saying, I received your packet, and then an ACK goes back. ACK is an acknowledgement packet that says, I received whatever you sent. Okay? So you have these three packet exchanges, and SYN, a reverse SYN, and ACKs, just to establish the connection. Nothing has happened so far. Only thing you've done is just establish the connection with the server. Once that is done, then you can actually send the request. That's the request the application wanted to send. That's the packet that's going to go over. And if that's the only thing the client wants to send, then it is going to say, I'm done. Okay, so you're going to send what's called a FIN. FIN says, I'm done communicating, so tear down the connection from me to the client, me to the server. Okay, so you'll send a request, you'll send a FIN. And an acknowledgement comes back saying, yes, I received the request. I also received your FIN message. Okay, and then the request is actually being processed. Once the request has been processed, an answer comes back. That's the response. Okay, and if that's again, since the client has done, it knows that there's nothing more coming. So you also send a FIN saying, I'm done as well. ACK goes back. Very standard, set up a TCP connection, send a request, get back a response, tear down the connection. Okay? 9 packets have been exchanged between the client and the server simply to send one request and get one response. Okay, so there are 2 real messages and 9 extra messages that is basically part of the TCP overhead of setting up the connection and tearing it down. This has to happen every time the client has to establish a connection with the server. And that's the way TCP works. So you will see that there is quite a bit of overhead just to send a message and get back a response. So people have looked at how to optimize this. This is a proposal that was made but never actually implemented in practice because it requires you to change how TCP works. Okay. This proposal basically allows you to batch. So you are not going to change the semantics of saying you need a SYN to set up a request or a FIN to tear it down, but you are going to allow batching of multiple messages that need to be sent. So in particular, the client will send one packet, okay? One data unit packet goes out over the network that includes a SYN, saying I want to set up a connection. It includes a request in that packet and it includes a FIN saying I'm done. All three things are sort of batched into one packet and sent over. So in one packet, you're told the server, I want to set up a connection. Here's a request I wanted to send to you, and here I'm done. Okay? And then the server can then process that request and send back a SYN in the reverse because it has to set up a connection in the reverse direction to communicate. And then in the same message, it will say, I got everything you sent until the FIN. That's an ACK. Okay, you send back the answer and says send a FIN. So you can batch those 4 messages and send them back, and then you get an ACK back. So you reduce those 9 messages to 3 and preserve the same semantics. Right? So this was a proposal to optimize the use of TCP for simple request response application. This will not work if you're setting up a long-lived connection or multiple packets have to be sent. Okay? If you are simply setting up the connection to send one packet request and get back a one packet response, this is a much more efficient way to do it. Okay? It only works for that specialized case, not for the general case where you want to, let's say, stream a movie. Okay, you may get millions of packets over the course of that movie. So that this won't work in that case because this connection will be long-lived, a lot of data will keep coming from the server. Yes.
Isn't that the reason why UDP is used when you've just got to send a small packet? Right.
Okay. The question is, isn't that the reason why UDP is used if you want to send one packet? So UDP is a sister protocol to TCP. It's a transport layer protocol, but it is not what is referred to as a reliable protocol in that it doesn't do whatever TCP does in terms of if packets are not reached, if acknowledgements are not received, the packet will be retransmitted. Okay, so every packet that is sent, you wait for some time. If an ACK does not come back, you assume the packet is lost, which is why you haven't heard back, and then you retransmit. All of these things are done for you by TCP. Okay? UDP is a much simpler protocol which just says best effort. Okay? Here's a packet. Okay, you don't do any extra bookkeeping. You don't track the packet was sent. You don't wait for an acknowledgement. You just simply send it. Okay? And the point that is being made is if you want to simplify this, then just use UDP. Okay? You could do that because in UDP there is no connection establishment over it. In UDP, you could simply send the first request out without doing anything. And suddenly a request would show up at the other end. Now, if you use UDP, you will not have all of this overhead, but you won't get the benefits of reliable transmission. So then the application would have to figure out what packets are sent, what were not received, and so on, and do the retransmission.
What about in the second case? So even in the second case, we're sending it in a single packet. So if that packet gets corrupted or something, then isn't that?
So the question is, what about the second case? So this is showing the scenario where no packets are lost. So there is only 3 messages. In the case the ACKs are not received, whatever you sent has to be retransmitted. So if this message doesn't come for some amount of timeout period, this client will send the original packet again. Okay, so that so if there are losses, the same packet will be sent multiple times. Okay, so that you will still get because it's TCP. Okay, so the reason UDP is not used over wide area networks is routers can drop your packet. So your packet may never reach the destination. So you do want the ability to retransmit and so on. Okay, UDP works much better in LAN environments where the network or the LAN is much more reliable, losses are rare. So you can get away with using UDP, okay, but not in the internet. Okay, so that's a discussion of TCP/IP protocol stacks and so on. Now we will actually move on to other issues which are related to communication in distributed systems. Okay, first I will talk about high-level architectures that you can use for communication. We already know that a popular way to construct an application is client-server. Okay, there's a client and there's a server. Okay, even within client-server, there are 2 modes of communication. Okay. The request response paradigm that I have been talking about, which is also quite popular, is referred to as the client pull architecture. In client pull, the client initiates the communication. It is the one, it sends a request and pulls a response back from the server. So that's why you're pulling. Okay, you send request for something, request for a web page, and you pull that data back as part of the response. So it's called client pull architecture. Okay, many protocols work this way, HTTP, FTP. So HTTP and HTTP server is not going to just deliver a page to you. You have to make a request first. Okay? It's called client push. The other mode of communication is referred to as server push. In server push, the client makes a one-time request for some data, and beyond that, the client doesn't send any more requests. And the server just starts sending data to the client asynchronously without any request for it. Okay. This mode of communication also is client server, and it is more appropriate for things like video streaming. Okay. In video streaming, you may just send the first request saying play this movie. Right? And then you just sit and listen on your socket, and the server is just streaming data to you. It is just keep on sending data. You just keep listening and you grab data as it arrives and you play it out. You don't say, give me the next chunk of data. You don't keep requesting this. Okay, you could have written a streaming application by simply requesting, oh, I played so much part of the movie, give me the next part. And you keep doing that. So that's not how streaming would typically work. You would use a server push architecture to do that. Okay? If you have like something like a stock ticker application where if you see business, not even business, you see CNN or some of these news channels, you'll see that they show you the stock prices. They just keep sort of scrolling down the bottom. Okay? And they keep getting updated as the price gets updated. That's another example where you just say, I am interested in these data items. Anytime the value changes, just send them to me. I'm not going to keep asking you every 10 seconds what's the price. Okay, that's another example where you can use the server push architecture. Okay. So client pull is the most prevalent one, because for many applications, the request response paradigm is the right one to use. But there is an entire class of application that's also client server that uses a server push mode of communication. Okay. So keep that in mind. Now, there are some pros and cons. If you have a choice, in most cases, you may have to pick one or the other. But for certain applications, you may be able to implement it either of those two ways. There are pros and cons of doing this. Okay. Client pull architectures are stateless servers. If you remember last time I was talking about stateful and stateless servers. So I said we'll come back and talk about this more. Okay, so here, when you don't actually keep track of which clients are interested in what data. You simply wait for clients to make requests or pull data, and you answer those requests. And then you are done as far as that client is concerned. If it wants more data, it makes more requests. In server push architecture, you are stateful because you keep track of what the client has requested. Okay, so once the client says play, you have to keep track of, okay, this client has asked me to play this movie out. It may be a 2-hour movie. So I need to keep track of what it has played so far and keep sending it more data. The client is not going to do anything. It's going to silently wait for data to arrive. Okay, so over the course of that session, the movie session, you are keeping state of that client at the server, because the server needs to keep track of what has happened. Same with stock ticker type application. You need to know what data is requested by what application and keep sending whenever the data is updated. Okay? So server push architectures tend to be stateful. They keep client state information. The stateful servers have less reliability than stateless servers. The server crashes or the machine is rebooted, because all of that state is stored in memory. If you reboot a streaming server, any ongoing session information is lost. Client will not see any more updates. In a stateless server, there is no state of the client. You'll see a brief downtime while the server is down. When the server reboots, you can start sending more requests and you can start pulling. The same as a web server. The website may appear down for a little bit of time, but when it comes back, you can start sending requests again. Okay. So here failures are easier to handle. Right? So failures are each. That should be easy to handle. And here they are more difficult because you will lose any state unless you keep state on disk. Keep state on disk, then you reboot a machine, your disk state is still there. You keep state in memory, because memory is volatile. When you reboot your machine or your application, if it crashes and restarts, anything that was in the memory of that previous process is gone. Okay, so assumption here is that the state is in memory. That is why it is less reliable. Okay, so that's basically a quick discussion of stateful and stateless. Yes.
Why are flexible architectures have limited scalability? Why do flexible architectures have limited scalability?
Why do client pool architectures have limited scalability? Okay, so I did not actually go into the scalability issues as much, but I can explain this a little bit. We would have come back to this when we did the web. So what happens in client pool architecture is for every small bit of information that the client wants, it's going to make a request. You have to incur the overhead of request processing and send back a response. Right? In the server push architecture, there's only one initial request. And then the server is simply streaming the data to you. You're not making any more requests. So the request processing overhead is going to be less. Right? There's still the overhead of sending data to the clients. And that overhead is not going to go away. But think of if you wrote a streaming application using client pool, you have, let's say, you're actually doing HD streaming, let's say, over Netflix. Right? So now you are going to make requests for 6 gigabytes of data in small chunks. Think of how many requests you have to send, how many requests have to be processed and sent back. Instead, if you just say play and your server is simply going to stream it to you, same with YouTube, that's much less request processing you will incur. That is the scalability issue. Okay, that alone. Any other questions? Again, the scalability aspects will come back to when we talk about web as an example of a distributed system further out into the course.
The example that you stated, for example, like YouTube, it's still unicast, right?
Is YouTube unicast? Yes, YouTube. So I haven't actually talked about group communication. That's the next slide here. So communication by default is mostly one-to-one. Okay, you have subsequent follow-on question, or what is your question?
In the sense, multicast would be even more scalable than the
Yes.
normal.
Okay. So I think the arguments here for client pull and server push still assume one-to-one communication. There's one client that's talking to a server, or one session has only one client. In the server push architecture, as has been rightly pointed out, you can do broadcast, or what is actually not broadcast but really technically multicast, where one send can reach multiple recipients. In this is referred to as group communication. Okay, in this case, you will get even further scalability. Rather than 100 clients making a request, you make one request and you send to a group. So group communication, the best way to understand that is same as a mailing list. Okay? When you send an email, typically you send it to one recipient. Okay? But if you send to a mailing list, you do one message, send one message, it goes to n recipients. Okay, that's one-to-many communication. Okay, that's an example of group communication. Same example, so the same idea of using mailing list is also available for real messages. Okay, you can send rather to one recipient, send to a group. So you only send the data once, and the network is responsible for delivering to all the members of the group. Okay? So the way this works is rather than sending to a specific IP address, you send to a special IP address. That's referred as a multicast IP address. Okay, so you just send to that address once. The network knows that that address is not one machine, it's actually a logical address that represents a group of machines. And it will deliver that message to all of those machines. Okay, that example of group communication is especially valid when you have streaming type scenarios. Let's say you're watching a live broadcast. Okay, that could be easily multicast. The server sends it once and then it reaches all the recipients that are subscribed to that event. Okay. But you can have group communication for simple messages as well. You don't need to use it only for server push. Even in client pull, or not even client pull, but any arbitrary application, you can send to a group address and it will reach multiple recipients. Okay. Now there are many issues in group communication which we will just simply gloss over for now. Okay. So issues involve, is the group static or dynamic? Okay, can you join a group midway through, let's say it's just you're watching a telecast of the Winter Olympics or something like this. Okay, if you join in the middle of the event, the group has changed. Okay, it's not going to be static over the course of the event. Okay. But you can have static groups where before the message goes out, the group is determined, and then over the course of the session, the group does not change. But in most cases, the group is dynamic. The group is dynamic, the network has to do something. Okay, every time a message comes out, it needs to figure out who are the active members of the group, where to send the packets to. Okay, so that can complicate how group messages are handled inside the network. Okay, groups could be closed or open, just like mailing list. You can say anyone can join the group, or some moderator decides who gets to be in the group. Same thing is true here. You can think about how the addressing works. I talked about multicast IP addresses, but there's also something called application level multicast, where the multicasting is handled at the application level by doing n unicasts by a middleware. Right? So you don't ask the network to deliver the message to a group, you simply give it to, that's where a middleware protocol would come in. You will ask your middleware saying, send this message to everyone in the group. What the middleware will do is it will send n unicast messages to the n members of the group. Okay, so you are emulating a group communication at the application level by using one-to-one communication at a middleware level. Is that clear? Okay, so your mailing list is an example of an application level multicast. Okay, you don't actually hand the email that you send the mailing list to the network and say give it. What happens is your mail server knows who is subscribed and it actually sends out n messages out. Okay, so that's the same thing here. Okay. And then there are issues of things like message ordering. If multiple messages are going out, some recipients are closer and others are further out. Should they see the messages in the same order? Okay. What happens if some messages get to the recipients faster than the other? All of these things will become important when we talk about protocols like distributed, commit, and so on. At the moment, it doesn't seem like you can go into an in-depth discussion on why message ordering is important and so on. Ideally, you want messages to be delivered in the same order they are sent. Okay, that's the right thing to do, but that may not always happen because of network dynamics, lost packets, and so on. Okay, because the packets are going out, one recipient may receive it, another recipient, the packet may get lost. Okay? But the next packet arrives, so now you received out of order packets and things like that. So that's all we'll talk about as far as group communication is concerned today, but we will come back to some of these issues later. Okay. So with that, we are going to now focus the rest of the class on remote procedure calls. Okay. Now, I don't know how many of you know what RPCs are. Has anybody programmed in RPCs? Very few. Okay. So we'll talk about what they are. Okay, and then I'll show you how to write some very simple code using RPCs. Your first programming assignment, you could potentially use RPCs, or if you in the Java world, they're referred to as RMIs, remote method invocation. Okay, because the first programming assignment will require you to write client-server application. So you'll have to figure out how you're going to do it. You can use vanilla sockets, you can use RPCs, you can use RMIs. Those are the choices you will have. Okay, so you need to understand what they are if you haven't used them before. Okay. So what is the goal of a remote procedure call system? Okay, the idea is you want to make distributed computing look like centralized computing as far as application design is concerned. Okay. So I assume that you all know how to write a simple centralized application. A single process would be multi-threaded or not. Okay. You know how to do that. You take your code, you partition it into functions. Okay, or you partition it into objects. Objects are methods, and then one method calls another method. So that's how you partition your code. Okay? And you know how to write those kinds of applications. What if you could write your application in the same exact way as you write a centralized application, but now you can also take advantage of distributed system. If you could do this, then as your application designer, you don't have to learn a whole lot of new other skills in order to write distributed code. You just write it as if it's centralized code. So how do you do that? Okay, so I mean, all that sounds great, but what does that mean? Okay. So what that means is you will still write your application as, let's say, collection of functions or collection of methods, okay, or objects, but some of these functions will actually now reside in a different process, potentially on a different machine. Okay. And what the underlying system will do for you automatically is when you call this function, it will know that this function, the code for this function doesn't reside in this process. Typically, when you call a function or a method, The code for the method is inside that process. Okay, you just simply go to that method and execute that method. Okay. Here, the code will not be in the process, but your system will know that, and it will actually construct a message and send it off to whichever process the code resides in, execute that process there, or rather the method there, and send back the results. Okay, this is why it's called a remote procedure call. The procedure, which is a function, resides remotely. The code is somewhere else. It's not in the function, and you're somehow invoking that code. Okay, so this is best shown by picture here. Okay, this is a client, the server. Okay, let's say you're simply calling a very trivial method which adds two integers and gives you the results of this. Okay. Typically, you will write the add method here. You will take the two arguments, sum them up, and return the result. Okay. But in a remote distributed application, you will basically write the add function and put it on a server somewhere. Okay. But here, you are not going to worry about. Typically, if you write a distributed application, you have to set up a connection with the server. All that code you have to write, and then send a message. How the message will be received, you will process it, you will do whatever the message requires and send back a response. Here you are not going to do any of that. You will not worry about the networking aspects at all. You will leave that to your RPC runtime, which is the middleware here. You simply call add as if it was a local function. The system will figure out that's a remote function. It will actually construct a message, send it here, okay, and actually execute add as if it was executing locally, get the response for you and return it back. That's basically what a remote procedure call is in a nutshell. It allows you to invoke procedures that reside in other processes on other systems. Okay. Now you do have to declare to the system that something is a remote procedure. It's not magically that you can't just call some random procedure in some random process. Okay. So when you write it, you have to say this is either a local or a remote. If it's remote, then the system will track it for you and make sure all the right things happen. Okay, but the interesting thing is that the amount of extra code you have to write to enable all of the communication between the client and the server is no longer your responsibility. The system will automatically generate that code for you. Okay, so we'll see how to do that. There will be special tools that will take your program and generate additional code that you would have normally written that will do all the communication, setting up the sockets and setting up the sending the messages, getting back the responses. All that still happens. There's still code for that, but it is automatically generated. You don't have to write that code. So now you program at a higher level of abstraction. You could have programmed at a raw socket level, in which case you write all of the code, including communication, figuring out where the client server is, all of that. Here, much of that code is automatically generated and the runtime system takes care of that for you. Okay. So basically the point is you want to use remote services to be called as procedures, and there are several issues we'll talk about. How to pass parameters from the client to the server, how to figure out where the server is, what happens if the message gets lost, and so on. Okay. Now there are two classes of RPC systems, those that are integrated into a language and those that are not. Okay. In the Java world, remote procedures, which they are referred to as remote methods there, are part of the Java language. Okay, they're built in. You can just use them. Okay. In C or C++ world, C doesn't actually have support for RPCs in the language. Okay, this is provided to you as a library. Okay, there is going to be an API that you will use, and then you will use that API to write the remote procedures and so on and so forth. Okay, but in either case, you can write code. It's just whether it's supported in the language or supported as additional libraries that you will use. Yeah, here's the same picture that I showed you, drawn on the board. So here's your client process. There's a server process. Okay, you want to basically invoke a remote procedure called add. Pass two arguments, the procedure will sum it up and send back some results. So here you are simply going to call add. That's it. Here is the implementation of add in the server process. Okay. When you call add, so everything above this line, black line here is the actual code you add. Everything below is code that is automatically created for you. Okay. So this is still code that's part of the client process, but you didn't write the code. Okay. Some tool generated it for you. Same with the server process. Okay. Everything above the black line is code that you write when you write the server. Anything below is the code that's generated. Any generated code is referred to as a stub. Okay, that's the terminology that's used in the C and C++ world. In the Java world, I think it's called a proxy. Okay, but this we'll just refer to as a stub code. Okay, so step one, client calls the remote procedure, Step 2, okay, the stub figures out this is not a local method, it's a remote method. It constructs a message. You will see it says call the procedure add. It has 2 arguments. They are integers. Here's the value of the first argument, value of the second argument. Constructed as a message. Message goes over a network. Okay. Message arrives at the other end. The stub says someone is trying to invoke add. Okay. So it processes the message. Someone is invoking add. They have given 2 arguments. Okay. So you will take the 2 arguments, actually invoke that function. Now because it's here, okay, the function will execute. It will produce a result. Same thing will happen in reverse. We'll construct a response, send it back to the stub. The stub will actually receive the response, and then this function will simply return a value as if you had called a local function, and it returned the sum of I plus j. Okay. Any questions here? All right. So now, as far as the semantics are concerned, okay, we'll see several different RPC semantics. The first one are standard blocking semantics. This looks exactly like you write centralized code. When you call a method, okay, or a function, you are basically going to start executing that function, okay, and then will eventually return back, and the original function will continue executing. That's how code works. Right? One function calls another, when you return, and you continue beyond where the first function was called. So if you think about it, the same thing is true in the client-server application. When you call add, the client will block. It will wait for add to return something before it continues executing. So this is standard blocking semantics, also referred to synchronous RPC. Okay, so this dotted line says that the client cannot execute because there is an outstanding function that it has called that is executing somewhere. Okay. So this is now going to trigger a message. Okay, then the server will execute, send back a result. When the result comes, you will continue execution as if the local add function, or not the local, but the add function that you called has executed and returned a value, and then you can continue. Okay. That's the same semantics that you see in a local procedure. You will basically, so the callee cannot continue until the caller has returned, typically. Right? So that's the same thing here. Okay, we'll see other semantics for RPCs, which are asynchronous RPCs next time. Okay, for today, we'll just assume standard RPC semantics are the same as calling local procedures. Okay, you block until the results are returned to you. So there's a note there about RPCs and the historical note really. So they were designed by a student, RPCs, designed by a student as part of a PhD thesis. Okay. Andrew Birrell was, I think, a PhD student. Actually, I don't know who was the student, who was the advisor. I'm assuming Birrell is the student. But I do have the PhD thesis with me if you're interested. They basically were designed as an idea by a student saying, why not let's us call for code that resides in another process, right, as functions. Okay, and then the student designed a system to do that, which was the very early form of an RPC. Subsequently, companies who were writing operating systems picked it up and they implemented commercial systems that not commercial but really products that implemented RPC systems and made it available widely so any programmer could use it. Okay? So now practically any version of Unix or even Windows ships with a built-in RPC system. You can just write RPC code, compile it, and use this kind of semantics to write distributed systems. I will put up a classical paper on the very first design of RPC, the paper that's referred to here. We'll see that is 1984, 30 years old. They were designed 30 years ago, okay, but now widely used in variety of forms. Okay. So with that background, I'm going to now talk a little bit about more in-depth issues that we have to think about. So now assume you know what RPCs are, but your job is really to write an RPC system as a distributed system designer, not to write RPC code as an application. Okay, so if you are a system designer and you are asked to write an RPC runtime system, what are the issues you need to deal with and how would you deal with them? Okay. First issue that you will have to deal with is how do you handle passing of parameters. Okay, functions have parameters or arguments, you pass these arguments. Okay. In a RPC system, passing parameters, as we will see, is more complicated issue. Okay. This is what will happen in a typical local procedure call. Okay, let's say you all know what a stack is, I assume, right? So basically, let's say some centralized application is executing, you call a function. The way it works is you basically take the arguments of the function, you push it onto the stack. You leave some value for a return address, and then basically the function starts executing, and within the function you will have its own argument. Okay? So this is basically how parameters will be passed. You will push them onto the stack, okay? And when the function executes, it takes the data from the stack, it processes them, sends a return value, and you pop the stack. This is basically how a typical function will execute. Okay? So you always push data onto the stack argument, you get the return value back from the stack. Okay? That's conventional procedure call. Okay, and in the conventional procedures or any system, you have two kinds of parameter passing, call by value and call by reference. In call by value, you will typically take the value of the parameter and push it onto the stack. Okay. In call by reference, you pass a pointer to the original data. Call by reference is the same as passing pointers. Call by value is you pass the value. So if you have an integer and you're passing the integer, if you do call by value, you just take the value of that integer and put it on the stack. And if you change that the argument, the original value will not change. In call by reference, you pass a pointer. So if you change the argument, the original value also changes. That's call by reference. Okay, that's pretty standard when you pass parameters. Okay. Now, when you basically have remote procedure calls, you will realize that call by reference is much harder to deal with. So think about what would happen if you pass a pointer as an argument to remote procedure. You will pass a pointer. You know how pointers work, right? What happens when you pass a pointer? What is a pointer rather? Let me not even ask what happens. What's a pointer?
Memory address.
Okay. Pointer is a memory address to some data item. Okay. Let's say you pass a pointer which is called by reference. You send that memory address over to the other side. You dereference this pointer on the server. Okay. What does that do?
So the memory on that machine instead of the older.
Yeah. So pointer is a memory address. So if you dereference the pointer on the server end, it will look up the that memory address on that server, which is meaningless because you are actually referring to the memory address on the client machine, not on the server machine. Okay? So passing by reference is basically not going to work when you have procedures, remote procedures. Okay? So typically, so that's one important distinction between local and remote procedures, is that you typically want to try to only stick to call by value. Value means you just take any variable, you copy its value over, and you send it. So in the add case, you take ij, you take their values, you stick them into the message, and you send it. That's not a problem. Okay, if you are passing an array, you'll take the entire array, make a copy of it, and you send it over a network. Okay, so every time you pass by value, you make a copy of whatever it is that you are sending over, and whether it's a simple variable or a complex data structure, you always make a copy and send. Okay. So call by value is the default scenario in remote procedures. So when you have remote procedures, many runtime systems will not allow you to pass references or send pointers because it doesn't work anymore. When we come to the Java world, we will see how to do call by reference. Call by reference requires you to chase network pointers. And now pointers are not memory addresses, pointers will have an IP address and a memory address on that machine. So when you dereference it, you will not look at your local address, you will try to look at the address on the machine from where the pointer came from. Okay. Much more complicated handling is required if you want to start dereferencing network pointers. Okay. So many systems will take the simple approach and say, let's not complicate the way the system works, let's only allow call by value. Okay. But we will see that in Java, you can actually do call by reference. And it will track where the reference came from, which machine it came from, and dereference it. When you dereference, it will go back to that machine. But that complexity is built in. It requires extra work. So by default, it won't be handled in most other RPC systems. Okay. So the other thing is global variables are also not allowed in remote procedures. Okay. Because the other function is executing in some other process. If you have a global variable in the client and inside the method you try to access that global variable, there are two different processes. It won't work anymore. Right? So you cannot pass by reference. You are not allowed to use global variables. So there will be some restriction. By and large, it will look like you're calling a local procedure, but with those restrictions in place because things don't work otherwise. Yeah. So we'll talk a little bit about stubs, and then I will show a very simple example of how RPC systems actually work, okay, real code. Okay. So the way things work is you will write your application, you will run it through some RPC compiler. The RPC compiler will generate the stubs, and the stubs will do all of the following for you. Okay? It is responsible for constructing the messages. It's responsible for what is referred to as packaging the arguments and doing something called marshalling and demarshalling of arguments. So what does marshalling means? So marshalling essentially is the process by which you can pack any data structure in a platform independent manner, receive it at the other end and recover the value. Okay. Now the reason this is important is RPC systems, when they are written, they do not make an assumption that the client and the server run on the same hardware or the same OS. They could run on arbitrary hardware. Okay. They don't have to be the same OS, don't have to be the same CPU, and none of that. Okay. We didn't make any of that assumption when we are talking about RPC. So what that means is the message needs to be interpreted at the other end properly. Okay. The simplest problem you can see is your architecture may be Little Indian or Big Indian. If you know what these are, Little Indian says that you read bits left to right, and Big Indian says you read right to left. If you simply stick an integer, which is a set of bits, and send it over, server happens to be not the same architecture. The other architecture will read them from the other way. So you send the bits over, but now they're misinterpreted. Okay. So how do you deal with that problem? Okay. Marshalling is supposed to take care of that for you. Okay. Same way, let's say you want to send a two-dimensional array. Okay. Should you send it row first or column first? If this client says I'm sending it row first and the server says I'm interpreting it column first, your array has gotten flipped. You have misinterpreted what was sent. Okay. So the client and the server need to agree on a set of rules which say that whenever you send even as simple things as integers, and certainly when you send more complex data structures, you interpret them and reconstruct them the right way. Okay. Once you agree on the set of rules, the marshalling process involves taking your data and sending it in the right fashion. Okay. Typically, you have what is called an external data representation called XDR. Okay. So you translate whatever native format you have into XDR format, you send it over, and then the server knows, regardless of what the client's data is coming in a standard XDR format, it retranslates them back. Okay. This is like two people who don't know the same language want to communicate. Okay. So what you do, every time you say something, you translate that into a third but standard language, and you translate it back. Okay. So there's no confusion. You always, when data comes to you, regardless of whether the client was Little Indian, Big Indian, Linux, Windows, it comes in the right format. XDR format is a known standard. There's no confusion whether it's Little Indian or Big Indian. So you will have to, in the stub, take whatever arguments you have, always translate them to a standard known format and then send them out. And at the reverse end, you are going to unpack it and retranslate it back to your native format. All that extra work has to happen simply because we want now platform independence. We don't want to say client and the server run on the same machine. Okay. When you send let's say an HTTP request to a server, web server, you don't assume that your server is running a Mac. It is going to work. It should work regardless whether it runs Linux or any operating system. Same is true here. When you call a procedure, you shouldn't make the assumption that the server runs the same OS as you do. Okay, you want it to work regardless. If you want it to work regardless, you have to do extra work to make it work. Okay? So the stub now, the good thing is, although we went into all of this discussion, the application programmer doesn't have to deal with any of this. They just simply call your function add. Okay? But if you're writing an RPC runtime system, you, the system designer, have to do all of this extra work in your stub code that you generate. Okay? So that all of the application designer's job is simplified. Okay? So you put more complexity into the system. Okay? So the way things will work is you will basically write a spec for, so this is a picture that shows the same thing. So you will have a client application, a server application, and you have a specification files that says, here are the remote procedures the server is actually going to export. Okay. You will take that specification file, you will run it through a special compiler called, in this case, in the C world, it's called Rpcgen, but it's really an IDL compiler. It takes an interface definition and it generates a bunch of extra code for you. This code includes the client stub, includes the XDR code, which is going to do all of the translation, it includes some header files and the server stub. Okay. So then what you do is you take your client code, you take the client stub, and you compile it together as if it was one application. So you think of it as somebody gave you the other part of the application that you did not write. Okay. Same thing with the server. You take the server code, the server stub, you compile it, and you get a server application. Okay. Is that clear? I'll show you an example that does exactly this. Question from yes.
So Rpcgen is run on the server and client both, or it's like run on either one?
Yeah, so the way it works is, in this case, you are assuming that you are writing both of these things, okay? And you're writing the spec. So the client, the Rpcgen would basically generate this. Okay? If the person who writes the client and the server are two different people, then what would happen is the person who wrote the server would say, these are the routines I export. You'll generate the stub code, and then somebody will give you the stub code for those functions. But in this case, we are assuming it's the same person or the same team is writing the client application and the server application, and then giving you the code. Okay, like if you write your lab, you will write the client and the server, the programming assignment, for instance. So you will have all of that code with you. Okay, so here's the same example, the add example. Okay, so you will see that there are some files that are here. There are 3 files. Okay, I don't know if this is visible. I'll make it a little bigger. Okay, so there is add.x, that's the spec. Okay, so this is simply saying add is a remote procedure. Okay, it is simply saying I have a remote procedure called add, and it has some extra things that you don't need to worry about. Okay, and then you'll see this is the add client. Okay, so here is so basically you do some extra, take the arguments for add, okay, which is the ing, and you're simply going to call add here. So you didn't do any network setup or things like that. You just called the RPC system saying I have set thing, do whatever you need to do, and here is an add. Okay, so you just called it. This looks like you called a local function because you didn't construct any messages or any of that. Okay, so here is the server, which is simply, that's a remote procedure that it has exported. It gets 2 arguments. It is simply adding them up and sending a result. That's all you write on the server side. You are not listening on socket, nothing. You're just writing 4 or 5 lines of code. Okay, so that's all you will write as an application programmer. Okay, so what then you will do is you will first do whatever I showed you. I'm going to run make here. Okay, first it will call Rpcgen. Just ignore all the warnings, but you will see that the first thing it did here is it called Rpcgen on add.x. Okay? And then it's starting to compile all of the code that was generated. So you will see now that there are a whole set of other files that got created. Okay, so there is that was your original client. Okay, there's a client stub, there's a server stub, there's some XDR code, and there's some header files. Okay? All is automatically generated for you. And then you'll just link them together and construct that's your client application, that's a server application that got created. Okay, so you can go, it's all C code, so you can actually look at it. Not this. Okay, so this is basically server side code. This is the server side stub. Okay, there's a lot of code you don't really need to worry about, but you'll see there's code to set up a connection, close down a connection, all that was actually generated for you. Okay. Here is basically code, the server side stub that says when somebody calls add, you'll do some XDR argument translation, all of that is also done. This is the marshalling and demarshalling of arguments. Okay. That's the main function for the server. Okay, you'll see that all the socket code is also generated for you. Because we didn't write main in the server, we just wrote add. The main function was generated for you. The socket code is here. Okay, and so on and so forth. Okay, I can give you the code if you want. You can take a look at. You don't really need to, as a programmer, you don't need to look at the stub code at all. it's generated, you just compile it in and you're done. Okay, but if you're interested in knowing what's happening underneath, you have to go look at it to see what's the stub doing and so on. Okay, so you can look at the XDR is not a whole lot because it's all in the library, but here is the simple XDR code that does the translation as needed. But this thing is then going to call a whole lot of other routines that are actually in the RPC runtime library that do the actual translation. So the standard ways to translate. Okay, same with the client. Okay, so here the stub code is very simple. It's simply calling the XDR code and then doing client call, which will actually set up the connection and so on. Okay. So I presume you get the idea. The point being that you don't put the burden of doing this on the end user. Okay, so exactly what I said, you have started with 3 files. The definition file that says this is the remote procedure, a client application that's simply called the remote procedure, and the server application that implemented that remote procedure. And then you ran this through the compiler, it generated all this additional code for it, the stub code, the XDR code, header files, which you then take and compile it in with the server, compile it in with the client, and you get 2 binaries that will then work. Okay? Questions? All right. So here are all the steps that are actually, that's the same thing as told you. So when you call the initial procedure, you'll call the client stub. Client stub will build the message, okay, hand it to the OS. The OS will send it to the remote machine because there's a socket connection. This remote machine will then receive the message, give it to the server stub. Server stub will process the message, call the actual code, then you'll construct a reply. You will send the reply back. So all the steps I showed you here are outlined here. So much of it is going to be done by the stub for you. You don't need to do. Okay. So I already talked about marshalling and demarshalling of argument, the little Indian, big Indian problem. So we'll not talk much about it. So I also talked about pointers. Okay, so as I said, there are 2 approaches. One is to prohibit the use of pointers, which is the default case. In C, you cannot pass pointers. It's not allowed. Okay. In Java, you have pass call by reference. That's one of the few languages that actually allow you to pass object references as arguments. Most of the RPC systems don't. Okay, Java is actually an exception, not the rule, and it allows you to chase pointers over a network. It has a concept of a network pointer. Okay? And when we talk about the RMI world next time, we'll talk about that in a little bit more detail. Okay? Last point in an RPC system is how do you find the server? Okay? Neither the client nor the server put any IP addresses. As you saw, there are no IP addresses in there. How do you find where the server resides? Okay? Typically what happens is you use what's called a binder, which is the same as a directory service. I think I mentioned this last time. Okay? What you will do is you will basically, the server will export its interface and register itself with the directory service. Okay, saying I am a server, I provide the add service. Okay? And the client, if it wants to call add, it will first talk to the directory service. Is there a server that provides the add service? Okay, is there one registered with you? And if yes, then tell me its IP address and the socket that I need to communicate with. The directory service will provide a response. Then the client stub will take the response and actually set up a connection. Okay. So this is basically how RPC systems will work. So you are not supposed to hard code anything. The server automatically a stub code that will register itself with a directory service. The client, the first RPC message, it will try to basically talk to the directory service and figure out where the server is. That's done one time. Okay, once you've figured out where the server is, don't need to keep talking to the directory service. I thought I had a picture somewhere here. So in the Unix world, the RPC directory service is called a port mapper. Okay, if you have RPC application running, you start seeing this process also executing on the machine. It started up on demand. Okay, whenever a server registers, it starts up and then it takes the registration and the client runs. Same thing will happen. You'll see there's a one-time registration step. The client asks the port mapper, gets a response, then communicates with the server. Okay. All of that code is actually in that there was a client create call and a server register call, you will see in the stub code. If you look at the stub code carefully that I was just showing you, those are the ones that register with the server and look up where the server is running. Okay, so last thing I wanted to talk about very briefly is what happens when there are failures. Okay, what happens if the message that the client sends to the server does not get there, it's lost. Okay. So there are two answers to this question. The first one is if you use reliable transport protocol, then you don't need to worry about it because the transport protocol takes care of lost messages. Okay, only lost messages, not server crashing. Right. So if you use TCP, if you are running RPC over TCP, and if you send a request and the message is not reached, it will retransmit. So the RPC system doesn't do anything. Once it hands it to TCP, it's TCP's job to get it over to the other end. As many transmissions or retransmissions are necessary, TCP will do it for you. Okay? Original versions of RPC, however, ran on UDP. Okay? Simply because they didn't want to pay that 9 message overhead that I showed you in the client server. Same thing will happen here. You will have 9 messages going back and forth for that one actual message to go and a response to come back. Okay. So since they didn't want to pay that price and original RPC systems were run for client server applications on local area network, they said why bother, run this over UDP. Okay. In UDP, however, if packets are lost, then it's the RPC runtime's job to figure out what to do. Okay, because the network is going to make a best effort to deliver the packet, but no guarantees. Okay, so then your RPC system has to take over. Okay. So now the RPC system that you have here can support either UDP or TCP. Okay, you can specify when you compile, you can pass an argument to the compiler saying either use UDP or TCP. Okay, there's always a default, but you can specify what you want. Okay, so if you use TCP, then the RPC system is built such that it won't worry about retransmissions and whatnot. If not, it will have to take care of it for you. Okay. So with that discussion, we'll talk about now what happens when there are various kinds of failure. First failure is server is not present. Okay, there's no server registered. You would ask the directory service, is there anybody providing the ad service? Directory service is no one who's registered that provides the service. Okay, there's nothing you can do in this case. You just have to return an error saying there's no such server. Okay. Now the other ones you can actually do something about. So what happens if there are lost request messages? Okay. So if you are using RPC or UDP, the request message was lost, the original call, then you will have a timeout mechanism. You will wait for some time. If reply hasn't come, you will resend, saying something did not reach the server, so I keep resending. Okay. Same thing what TCP would have done for you, now you do at the RPC runtime system if you run over UDP. If you run over TCP, this will not occur at all. Okay. Now what happens if the message reached the server? Server processed the message, but the reply was lost. What would you do? Okay, again, if you ran over TCP, that will not happen because the TCP will keep retransmitting. But let's say you are not using a reliable transport protocol, you are using UDP. What would you do in the runtime system? Okay, so simplest thing you can do is resend the request. Okay, I did not get a reply, so I just simply say, okay, execute the procedure again and send back a reply. That's the right thing to do. However, you have to be careful when you do this because if your request changes the state at a server, sending the request twice may change that state twice. Okay? If your RPC request, very simple example is your RPC request increments a counter. Okay, all that you're doing is you're just saying increment a counter. That's your RPC method. Okay, the first request did reach it, incremented the counter. Okay, but the reply was lost. Now you retransmit that request. Okay, you will increment the counter again. That's not the intended the intended response you're supposed to see at the server. Okay, because now you ended up doing this operation twice instead of once. Same is true for any RPC request that changes state at the server. So what you want is, you want your system to do, make idempotent operation. Idempotent operation as idempotency basically says no matter how many times you execute the request, it has the same end result. End result shouldn't depend on how many times the request was executed. a very important property that you need in systems where if you retransmit requests and make the same procedure execute twice, you don't want the wrong result to show up at the server. Okay. Think about if let's say you're making a travel booking, and you're using RPC system. Okay, you say book a plane ticket. Okay, server books a plane ticket, but the response saying I did it, lost. Okay. Send another request. Server books another plane ticket. Now you have 2 tickets. Okay. That's not what you intended to do. So that's the same kind of stuff that will happen here. So you want idempotency, which basically allows you to track was that request previously received and already processed. In which case you don't execute it again, you buffer the result and simply retransmit the result. Okay, that's how you'll implement idempotency in your system. You'll have to assign IDs to every request that is coming in. Okay, and you'll say, when a new request comes in, did I actually receive this request previously? Have I already executed it? If so, I'm not going to execute it. I'm going to simply say what happened the previous time I executed it and just send back the results of that operation. Okay? So you need to make requests idempotent. You'll need to add sequence numbers. So your system will get quite complicated. Okay? So
what if you got a request that was actually new but looked similar enough that you wouldn't?
Okay, good point. What if you got a request that was new but actually looked like a previous request? What would you do? Okay, so in some sense, you don't look at the request itself to figure out whether you received it or not. You will add an ID, a unique ID to a request, which will allow you to track it. Because you can't just look at a request saying, did Arman try to book a plane ticket? Because you may want to book 2 tickets. You may want to take somebody from your family. Right? So you will not do that. You will actually assign a unique ID to every request and track requests that way, not look at the contents of the request itself. Okay, so you have to be smart. Yeah, you have to do the right thing, otherwise your system will not work. Okay. So that's the ROS replies. Now you can also have servers failing. The server goes down in the middle of processing a request. What should you do? Okay, in this case, the request will be sent again, but then you have to basically figure out what the response. If you get a response from the server, what does it mean? So you could have a guarantee that when a server response comes back, you have what are referred to as at most once semantics. That means you're guaranteed the server actually executed your request at most once. Okay? You can have exactly one semantics, which is exactly once. You can have at least one semantics. So a response came back. I don't know how many times I executed this, but I executed it at least once. That's why you have a response. Okay? If you don't have idempotent operation, at least one semantics will cause you trouble. Because it says to get a response, I may have executed this request multiple times, so it may cause some state changes at the server that may cause unintended consequences. So what you would like to shoot for is exactly one semantics. Whenever a reply comes back, I'm guaranteed the procedure executed once and only once. Okay? At most once is easy, because you can say 0. If the reply is an error, I couldn't execute it. Okay? So at least once is risky. At exactly once is the right thing, but most hard to achieve because you have to do all sorts of extra bookkeeping. Okay. So we have some slides on what happens when the client fails, but I will wait for next time to talk about that. We'll end today. We ran out of time. So this overflow slide we'll talk about next time.